built himself a shortwave receiver with valves and one of these Electronics Australia kits that was that he built back in the 70s, and I loved it. I just loved it, and I still have it too, by the way. And it doesn't work at the moment, but anyway, so I used to turn the dial and just listen to all these things on the shortwave radio, and it was I had a fascination for what was out there. But the thing that got to me most was the clock transmissions, in particular the 4.5, 7.5 and 12 megahertz coming out of Lyndhurst, Victoria, Australia, V&G. And I always, that was the thing that got me as a kid, and I always was fascinated by time. And then when I got my first digital watch when I was about 15 or something, that was just so exciting. I've always been fascinated by time, and accurate time. So anyway, the years go past, I get myself a degree in computer science and mathematics. So I was always good with computers, so that was just a natural degree to get, but I got the maths for fun. And then I went out and got a job, had a family, and did all that sort of stuff. And so the story goes, and this is actually a fairly interesting story, so I will sort of talk about it in full. I worked for Telstra, and don't hold it against me, but they are a really good company to work for, and they do look after their employees. And anyway, I started delving around on the Telstra internet because I was interested in the speaking clock. 1194, and you get the speaking clock on the phone. And so I started delving around, and there was this site, Telstra Research Labs, which was a part of Telstra where people would design and build stuff. This was back in the old days. That would have been, all of you would have loved to have worked there. It was just where a lot of ingenuity was created, and it was a really exciting place to work. But anyway, they closed it down because that wasn't what Telstra was. We're a telecommunications company now. So anyway, they had this website, this is internal to Telstra, and I was scrolling through it, and they were talking about when they first brought on the speaking clock and what it was and what it replaced and all this sort of stuff. And anyway, I found all these list of names in there, and I sort of got this list of names from the 70s, and I sort of printed them out, and then I went through the current Telstra thing and just typed each name in to see if anyone was still working for the company, and I found one name. And so I gave him a call, and I said, no, I shot him an email, and I said, Graham, I just want to have a chat to you about, the speaking clock and everything else that's happening in Telstra. I just, want to know a bit more about it. I find it fascinating. And he said, no worries, give me a call, but make it quick, as in do it soon. That's a bit odd. So anyway, I rang him up, and we got on the chat, and had a long chat. And it turns out he'd been made redundant. He couldn't tell me at the time, but he'd been made redundant. He was going to leave literally in 2 days' time, so that's why he said make it quick. So we had a bit of a chat about the speaking clock and all the bits and pieces, and the V&G that I was talking about before, the synchronisation for that came from the Telstra Labs in Melbourne, and the season clock that they had in there. So he was telling me all this sort of stuff, and that was that. Anyway, he retired, was made redundant, and took a package, and that was it. So anyway, it was about a year later, out came an announcement that the Telstra was getting out of the speaking clock business, and there was one of these units in each state. And I sort of thought to myself, well, that thing will end up on the tip. I'm not going to let that happen. I need to, make sure it goes to good home, i.e. mine. And so anyway, I dug around, found the project manager who was managing this decommissioning project, sent him an email saying, look, I don't know what your plans to do with it, but if it's going to go on the tip, let me take it away. Anyway, so that was fine. He shot me an email, said, yes, Jim, no worries, we'll organise it. We'll see what we can do. So a few months later, I get a phone call, and it was Graham, the guy I'd been speaking to 12 months prior, and he said they put me in charge of sending everything to good homes. So the whole thing came around, and so I got the speaking clock. And I have kept it running in my garage since that time. That was, when did I? Probably 2012, it'd have to be 2005, so I probably had it 6 or 7 years, I think now, and I've kept it going. I've kept it going quite regularly. It's pretty much continuously, apart from moving house and the odd power failure. It's an amazing device. It's all digital, but it's the old TTL sort of digital stuff. So, and it's the size of that unit there, really. It's a fridge. And but it's broken down into various bits and pieces, and it is built like a tank, like it's German made, and it is designed never to fail. And they have multiple. Every unit has got two of each, so that they all fail over automatically. So if one unit goes, anyway, the way it worked was that it got its synchronisation from Melbourne, because the cesium standards that are used, particularly the HP cesiums, which is ones that are fairly standard to be used for timing, are very expensive, and the cesium tube that's inside them wears out after a while, maybe 10 years, 15 years or something like that, and to replace them is $30,000 or something like that. This was one of the reasons Telstra got out of the business, because they had to keep supporting these atomic clocks, which were very expensive. So there was a couple of those in the labs at Telstra, and that's where V&G, before it closed down, got its stuff, and that's where all the speaking clock got its signal from. Now the way this was sort of fairly interesting, or I find it interesting, and I'm assuming you lots will too, but there was no cesium standards in any of the exchanges in Hobart or in Sydney or any of the other places. It was all transmitted over the phone lines. So there was a phone line between the Melbourne labs and say Hobart, just a normal phone line, and the accuracy of the speaking clock, which was very accurate, was transmitted over the phone line, using a sort of a thing that Telstra Research Labs built. Now, of course, all that's gone. So I couldn't just plug into that and use it. So I had to hack this thing to try and get. My goal was to have it being accurate. So I acquired a GPS discipline clock, which I'll talk a bit about later of those, and I'm sure you'll know about them, but we'll talk a bit about those too. And I acquired one of those, and with a bit of hot wiring and a bit of help from Graham, he said, you need to insert it at this point in the circuitry, and because they all came with manuals, all circuit diagrams, everything, so it's fully serviceable, which I just love, and they have needed servicing. And anyway, the bottom line is I got it linked up, so I got a 1 pulse per second signal coming out of the GPS and into the speaking clock, and lo and behold, it's there keeping perfect time. And just for a bit of extra fun, I thought, right, I'll go and grab myself one of those tiny little J-car transmitters that you can buy over the counter, and I'll just transmit it around the house so I can have it on the radio. And I lived in South Hobart at the time, and it was a bit up on the hill. And I was driving, I think I was driving over the bridge, and I set it to 107.7 on the FM band, right at the end. I was driving over the bridge one day, and I heard it, and I thought, what? And there's these certain key spots, if you're really, on top of the mountain, because I was in South Hobart, that was easy to get up there. And there was these certain key spots, and I thought, ooh. I didn't realise how far these things could transmit.
Is it still in the same frequency?
It's still the same frequency, but I've moved house, you see. It's at one divorce later, so maybe I shouldn't tell you. Maybe leave you as a little track me down. No, I live in Old Beach, but I am on the hill, so you'll probably find out the northern suburbs, even on the western shore. You'll probably even pick it up if you've got good antenna. So yes, it's transmitting, and the promise I make to you is it's always accurate. When the leap second happened a few days ago, and I had it all configured in there, so cut over to the leap second like that. And just for the other little bit of just a bit of fun, I got one of those old Bakelite telephones from an antique shop and had it sitting next to it. You can pick up the Bakelite telephone and listen to the speaker. So anyway, I have a few photos and stuff in here, so I'll show you that. So that's sort of, I love timing. And anyway, what happened was, I was showing my partner, I was just one weekend, everything was closed, and I was just walking around the university, and I was just, oh yeah, that's where I did all my lectures in there, and blah 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 blah, about when I got my degree back in 84 and 85 was when I finished and got my degree and my honours degree in computer science. And I sort of got the itch, I thought, oh, I wouldn't mind doing something again. And ironically, just around that time, I'd started this course. I can't remember where the guy was based. I'd know the name if you said it, but it was a radio amateurs course, so it was a training course and I did all 20 lessons and did all my 20 assignments, and then my marriage fell apart, so I never took it any further because I was actually interested in getting my licence. But anyway, I was wandering around the university, And I got the itch, and I thought, oh, and I was on holidays, and so I just decided, no, I'm just going to walk in. And I just walked in and said, look, I think I want to do something, I don't know what. And I ended up talking to Professor John Dickey. And he goes, well, what interests you? And he goes, well, I love clocks and accurate timing and stuff. He goes, you need to study pulsars. So that's what he said. And so I said, okay. So all of a sudden, when I was younger, I was a vice president of the Astronomical Society of Tasmania, and I love my astronomy, and I still do, but all optical. And all of a sudden, I was presented with this radio thing, this dish, and I had, it was quite a bit of a learning curve there, and especially a learning curve about pulsars, because I got my degree in computer science and mathematics, but because I had the degree in mathematics, they allowed me to go into physics. So that was pretty nice. So anyway, I'm going to just sort of ramble on and talk about stuff. So feel free to ask some questions anytime you want. But I'm going to talk a bit about my research, because I just handed in. I did it part-time, so I had a full-time job, and I was working full-time job when I was doing the masters part-time. So it was over 4 years, and I literally handed the thesis in about 3 weeks ago. So in that last 2 months, just leading up to the end, was just so hard, but really good. So what is a pulsar? What's all this about? Well, I'm going to talk about the life of a star. So well, actually no, we'll get on. That's on another later slide. So I'll start here. It was discovered by Jocelyn Bell Burnell and Anthony Hewish in 1967. Now, what happened here was Jocelyn Bell at the time she was called, was the equivalent of me, was the sort of research student, and Anthony Hewish was the PhD, the professor or whatever at the time. Anyway, she made these discoveries of these little pulses on the radio telescope, and that turned out they were thought to be of human origin, because obviously if you see something pulsing away on a radio, you're not going to think it's coming from out there. But what they found was that the direction from which it was coming would move by 4 minutes each day. So they pointed there, and then it'd be 4 minutes later before it came past. Now that's sidereal time. That means because the Earth is going around the Sun, the same spot in the sky takes an extra 4 minutes each day to get back to that same spot, and that instantly says that it's not of earthly origin. So they called it LGM1, standing for Little Green Men 1. And as it turned out later on down the track, the Nobel Prize was awarded for that discovery to Anthony Hewish, even though Jocelyn Bell was the one who discovered it. And so we in the pulsar community, we always look after Jocelyn Bell, and we always mention her whenever we can, because she was the discoverer. Apparently that was, back then, that was the thing you did. Your undergraduates you didn't get Nobel Prizes, but they do now. They changed the rules on that one. So what is a neutron star? Okay, so a neutron star is a rapidly rotating, highly magnetised, incredibly magnetised star at the end of its life. And I'll cover more of the details of how it gets created a bit later, but they start off large, like our sun, or bigger, but they crush down to about 20 kilometres in diameter, which is very small for a star. Now, some of these stars spin very fast. They spin fast when they're first created, and then they slow down over time. And in fact, that is the fastest one. When I put that slide together, this is a talk I gave about a year ago. They've actually found a faster one now. It's about 750 hertz. So it spins 750 times a second, if you think about that, as far as an object that's 20 kilometres across. Is incredibly fast. The other little piece of information, we've got a new satellite up there called Kepler at the moment that's discovering extrasolar planets, as in planets around other stars, not our star. And the way it does that, it's extremely sensitive to light, levels of light. So it can point it at a star, and if there's the star, and if there's a planet, the planet will pass in front of the star, and the light level will dim a tiny, tiny fraction, but it's sensitive enough to pick it up. And not only that, when it goes around this side, it's reflecting the light off here, going out there, so the light level increases as it comes around here, and then it drops again as it goes behind. So this Kepler can pick this up, and it's discovered in the last 2 years, I think it's 750 extrasolar planets. The very, very first one was discovered around a pulsar. Now the beauty of pulsars is they send out these pulses, and we'll get to what's happening there in a minute, but they send out these pulses. Now if you've got pulses shooting across the cosmos through the galaxy and we're picking it up, they're very sensitive and they're very accurate, and they can be measured against atomic clocks, and so you can time these things very, very accurately. And if they change at all, you can pick it up very easily. Like I'm measuring them down to an accuracy of about 11 microseconds. So the resolution of the pulse is about 10.9 microseconds. So we're measuring them incredibly accurately. Now, that means if there's anything funny going on, like a planet orbiting the pulsar, that's going to change the pulses in a very subtle way, and that's how they picked it up. That's not what this talk is about. Okay, so that's fine, but what really is a pulsar? So, I'm going to talk a little bit about the life of a star. At the start of the life of a star, it's just a whole bunch of hydrogen just sort of floating around. And there's little extra bits, more here and less here. There's clumps. It's not just a homogeneous, smooth thing. It's sort of clumpy. And these little clumps of hydrogen have a tiny little bit of gravity with them, caused by the Higgs boson that we had announced tonight, which is big news. Tiny bit of gravity which attracts a little bit more hydrogen to them, and these clumps sort of get bigger and bigger and bigger, and more hydrogen starts coming towards them. As this happens, they get bigger and bigger and bigger, and it starts to warm up, and they get heavier, attract more hydrogen, and this is the sort of the proto sort of birth stage of a star. And once it gets to a certain temperature, you get what's called a fusion reaction occurs. So you've got gravity pulling it in, and it heats up and heats up and heats up, and there's enough heat and pressure in there that fusion occurs. Now, you've heard of nuclear fission, I'm sure, with the atomic bomb and nuclear energy. That's where atoms are split and they give off energy. Well, fusion's pretty much the opposite. They're fused together. So the hydrogen atoms get pushed together and they form helium. So it's a move from hydrogen to helium, and we call it burning. Really, it's not burning in the strict sense, but it moves from hydrogen to helium and gives off energy. Now, so what you've got now is you've got gravity pulling the star down, and I shouldn't call it a star yet because it's not quite a star. And then then you've got the fusion reaction started up now, and it's pushing out, and these two wave around a bit and settle down, and after a few hundred million years, it sort of settles down and it has a star, and there's a star sort of form. So as you've got this ball of hydrogen that's a fusion reactor converting the stuff to helium, pushing out, gravity's pulling in, it all sits down, and you've got a star. Now, our star is just a bit before 5 billion years old, and this is the life cycle of our sun, so it's about halfway through. So as you ticks along, the hydrogen gets converted to helium, and the hydrogen eventually will run out. And this is where things get quite interesting, because the hydrogen runs out, gravity wins at this point. Gravity is continuous, fuel runs out, so it crashes back down in again. Now what happens there is the hydrogen is gone, and the helium now gets crushed into the next level of fusion reaction begins, and helium goes into lithium, I think is the next one it goes to. Now, and then it starts up again, and it's getting on now. It sort of starts to expand out, and all this sort of weird stuff starts to happen, and all these heavier elements start being created by this fusion. So when the helium runs out, then the lithium will take over, and then the lithium, and then eventually it gets down to iron, and that's the last one. And then you can't have a fusion reaction with iron, and so at that point, gravity wins completely. Now, depending on the size of the star, depends on what happens at this point. If it was a fairly small star like our sun, 1 solar mass, it would just fizzle out and just sit there, and it would just become what's called a white dwarf, and that'll eventually fade out and become a brown dwarf, and then ultimately in a few thousand billion years will become what's called a black dwarf, and just sitting there. We're not interested in that, we're not going to talk about that. On the other side of the spectrum, if it's very large, greater than about 5 solar masses, a black hole is formed, and I'll come back and talk a bit about that in a minute. But if it's this nice little sort of mummy bear size, sort of 3 to 5 solar masses, what happens is basically you get a supernova. Well, the supernova occurs if it's 3 solar masses or more. So the gravity wins, and gravity is so strong because of the mass of everything, it crushes everything down, and it's so strong that it actually forces the electrons that are around the atom into the nucleus of the atom. And if you remember back to your basic chemistry and physics, you've got an atom, it's got a proton in the middle and a neutron, protons and neutrons in the nucleus, and then electrons whizzing around. The electrons get forced into the nucleus, they combine with the protons that are there, and electron plus proton is a neutron, and so then you're just left with neutrons, and all that gap is gone, so the density increases incredibly. So you have this incredibly dense star. Now, when the supernova occurs, by the way, once the gravity wins, it sort of, and this happens within hours. This supernova, it just goes from there and it crashes down and it explodes in a massive, massive explosion, and massive amount of stuff gets given off, massive amount of light, and then that all spreads out into these magnificent nebulas and all that we'll get to see some photos of. Actually, yes, I think I've got one here. So, and then what's left over is then crashed down into the neutron star. Now, the neutron star, our sun, you may not be aware of this, but our sun actually spins on its axis about once a month. And so sunspots that are on there, they'll rotate around and come back around in about a month and reappear. And when they do that, when they sort of sneak around from around the side, and then if the sunspots, if there's a lot of solar activity occurring, we will get quite a bit of radiation hitting the Earth, and I'm sure you guys are aware of this. You've been monitoring this pretty closely, I would expect. Yes? Yes. So yeah, the sun's pretty active at the moment. It goes through 11-year cycles. There's a really good iPhone app for it, by the way, called 3D Sun. And you get these little notifications when solar flares occur. So
Space Weather.com is a good one as well.
Yes, no,
Yeah.
This is portable. This is
it's
an app. It just pops up. I wake up in the morning and says, "Oh, we had it this morning. There was a new flare." So I had to watch out for, keep an eye out for auroras. Now, if the star happens to be greater than 5 solar masses, then something interesting happens. So, the only difference between a neutron star and a black hole is escape velocity. Now, if I pick up a rock and throw it in the air, it's going to fall back down. If I shoot a bullet into the air, it's going to fall back down. But if you can propel something with enough velocity, it will escape the Earth's orbit, and that's called escape velocity. Now the problem is in this scenario here, is that once you get above about 5 solar masses, the escape velocity of the object, of that neutron star as it is greater than the speed of light. And so light itself gets sucked back down. And effectively it means we can't see what's in it. And so then a whole new world opens up there and that's black holes. So that's not what I'm discovering, not what I'm talking about here tonight, but that's the difference between a black hole and a neutron star. So one could argue that the neutron star is the black hole we can see because the escape velocity is not strong enough to stop the light escaping or the electromagnetic radiation. But of course once you are over this limit and it becomes a black hole, nothing escapes, and so the physics inside no doubt changes. And look, that's a whole other thing, but that's not what I'm here about. I've covered this about white dwarfs. I'm not going to really talk about white dwarfs because we're talking about pulsars, black holes and atomic clocks. And here's an artist's impression of a black hole, which I thought was quite cool. Yeah, probably. Because you can't really see one, but I think I've got a real one here. This is probably the closest to what we can sort of think of what a black hole might look like. Even though a black hole's black and technically black and sucking stuff into it, it does actually give off radiation, so we wouldn't actually see it as black from our distance. But this is a fascinating photograph because heavy objects, gravity warps space-time. So light, if you've got a heavy object here, light will curve around it, okay, as it travels past it. And that means if you've got a heavy enough object, it will behave like a lens. And so theoretically, you should be able to see things out there that look like you should be able to see as if you're looking through a lens, okay? And that's what this photo is showing here. You can see you've got these sort of strange curvy, up there, see how you've got these strange curvy things? You can't really see it, there is one there inside that thing. And that's because there's a black hole there, and that is, these are actually distant galaxies that have been bent around and observed. And it's actually like acting like a lens of however far away that is. So, yeah, quite fascinating. Again, nothing to do with pulsars and so on, but really good photograph.
So, at the centre of all those arcs, that's where the black hole is.
The black hole is acting like a gravity lens, so it'll be around here somewhere, and we can't really see it. And these are all these galaxies, okay? And these bendy parts are other galaxies that we can't see that are beyond there and a long way away, but this is acting as a lens, and so it's like magnifying, like a telescope. Okay, yeah, I think I've covered this one. What's inside a black hole? Don't know. But we're going to look at neutron stars and pulsars because we can look at them. So, supernova has occurred. The core has collapsed right down. It's spinning really fast. Oh, it takes about a month to spin, but when it's gone from 1,000 Earths across or bigger, crushed down to 20 kilometres across, you get the conservation of angular momentum, which, you know, when an ice skater pulls her arms in, she'll start spinning really fast. So your once a month rotation turns into your 700 times a second or whatever. Now, the pulsar has extremely strong magnetic field, and it's spinning, but the magnetic poles, like the Earth here, aren't necessarily pointing in line with the equator, with the rotational poles. They could be anywhere. So it's like you've got this spinning magnet. Now, the radiation, because the thing's spinning so fast, radiation can't really escape it. It travels along the magnetic field lines and gets sucked back in again. It only comes out from the north or south magnetic pole. And so if this thing is spinning and the north pole, say, for argument's sake, just happens to pass across the Earth, we'll get a flash, electromagnetic flash. And we can see it in radio, in gamma rays, and they're very faint, but you can see them invisibly if you...
Are they any particular frequency?
Yes, yeah, we'll talk about that. So there's, again, an artist's impression. So this thing is spinning very fast on that line there, and then there's the magnetic fields there, and then all the stuff is spewing out that way, and if that happens to be one of those happen to pass across our line of sight, then we see a brief flash. So that's what it looks like. So this is this is from the radio telescope, but this is some very, very early data. This is probably one of the first pulses I ever looked at. And actually, I'm at 4,800 megahertz. Like I was looking to see, like in science, when you're doing stuff like this, you don't necessarily just take everybody's word. You know, if it might be well established that the pulsar is stronger at 1,400 megahertz. But no, I wanted to go off and look at 4,800, you know, and you can do that, and that's fine. It's really, you know, nothing wrong with challenging. In fact, science is all about challenging what's happening there, you know, what the current beliefs are. So I was looking at, it's a bit high frequency for the Vela pulsar. Now this is the Vela pulsar. It's called that because it's in the constellation Vela. It was a supernova. It's about 1,000 light years away, and it's very well placed in the southern hemisphere, and it's the brightest pulsar in a radio sense in the southern sky, and so it's a beautiful target for us to look at. Now typically single pulses in observing single pulses, unless you've got a really big telescope, is a hard thing to do because they just get lost in the noise. Now, so what you normally do is you observe lots and lots and lots of pulses over a long period of time and add them up. And then you can get what's called a sort of an average pulse curve, if you like. And everyone does that, because you can do that with any size telescope just about. But to see single pulses, you need something you either need a very bright pulsar or you need a very big telescope. So the Vela pulsar is pretty much the only pulsar that we can look at with the radio telescope at Richmond. So that's a single pulse that you're looking at there. Yeah, I think the next. So that's magnified in. So let's go back and just put this in perspective. So Vela rotates 11.1 times a second, or 11.2, so 89.3 millisecond. So this is a time graph going across there, and there's the pulse. And we typically wrap it around in the period of the pulsar, and that's basically the flux coming in, and there's the frequency at the top. And JO at 35 minus 4510, that's its designation. And 0835 is its right ascension, and minus 4510 is its declination, if you're interested. So now we zoom in. So instead of going 0 to 89 milliseconds, we're zooming in from 57.5 to 58.5. So that's the same pulse, magnified. So now each one of these points, now that you'll see there's little jaggities going along here, 10.9 microsecond resolution there. But you can see you've got some interesting microstructure, and it's it's almost a double peak, and that was a little bit intriguing as to why that is. So, actually, I'll take that. I'll go back there first. Now, I just need to explain something. Now, Vela was known for producing these pulses, flash, 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 and then every now and again it does a really bright pulse. Okay, so it's just 10 times brighter than normal, just out of the blue, and quite well known. It's been sort of studied, but no one had really studied bright pulses in Vela very much. And so what we decided, I saw these bright pulses and I thought these look interesting, and it was sort of, I was told, yes, that's a good path to take because there's not much known about it. So I was doing part-time, 4 years, so they said, right, let's do a long study. So what we ended up doing was I'd go out to the Richmond telescope once a week, typically, weather permitting. It can be day and night. I observed when Vela was highest in the sky as best I could. It was wind that was our killer. So if ever it was windy, we'd have to shut the telescope down, and so spring was a terrible time for observing. So I picked 1440 megahertz because that's where Vela is pretty bright, and there wasn't much radio interference happening around that time. And I'd go out there for about 4 hours each week. And so I'd do a 4-hour stint, record single pulse recording, and do that every week for 4 years. So that was the plan. Pretty much came, and what I ended up getting was 10 million pulses recorded. It's the longest single pulse study ever done in the world. Because the thing is, with the big telescopes, at Parkes and all the other ones around the world, you get your half an hour on there when you're doing your PhD, and you write your PhD on that half hour of observation, because there's a queue a mile long to get in there and get there. So we're really lucky down here. We've got a fantastic radio astronomy program. The one thing you can get on this thing is time. You have to work around the students and various other things that are happening, but if you can be flexible, you can gather a lot of data. And I did gather a lot of data, 640 megabytes every 10 seconds. Okay, so there's an enormous amount of processing that has to be done afterwards on that data. And anyway, I was looking for these bright pulses, and in fact, I had my first conference in Sydney. I'd only just started on a preliminary bit of data, and everyone has to give a talk at these conferences. And believe me, scientific conferences are, if you're faint of heart, you don't want to be giving a talk, because it's not a sort of a friendly atmosphere like this. It is, how do you know that? Why do you know that? They literally try and tear you apart. I mean, you go and have a beer afterwards, but they will, any weaknesses in what you're saying, you can't just say, oh, because I think it's a good idea, or I've got a hunch, or whatever. No. So that was a real wake-up call, and in fact I was at a later conference at Molonglo. I was giving a talk, and I was asked a question I didn't know the answer. Now, I worked in public service for 15 years, and I worked for Telstra, so I sort of fudged it. I didn't make something up, but I sort of did what you do in business and government. You fluff around it, and people move on, and that was the biggest mistake I ever made. I got ripped apart, and I sat down at dinner at night feeling just terrible. I sat next to this very young, she looked 12, but she wasn't. She was 20 or something like that, and doing a PhD. And she said, So how do you think your talk went, Jim? And I said, oh, not really good. And she said, you know what you have to say? You know all you had to say then? And I said, what? And she said, I don't know. I thought, That's all I had to say, because I was asked the question, I didn't know the answer. It's fine. You say, I don't know. End of story. But you don't. I'd never do that to my boss. So I learnt that one, and I was asked a question later on at another conference, and I said, I don't know. And everyone goes, okay. So, anyway, back to consecutive bright pulses. I was looking for these bright pulses. I was at this conference, and I put up a slide showing a bright pulse I'd found, and someone commented, turns out he was very famous in the pulsar world, and he goes, there's 2 in a row there. That's interesting. You should study that. So I thought, ooh, Dick Manchester said that, I'm going to study it. So I really had to focus now. So what I was looking for was bright pulses happening one after the other. So it's flash, 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 bright, bright, 2 in a row. And so I gathered a bit of data at that point, and so I wrote some software to analyse that data and hunt for these bright pulses. And now the slide, what happened was, this was amazing. I had all these files which I knew had bright pulses, consecutive bright pulses in them. Thousands of them. And I had to go through and look at them all at some point or whatever. Anyway, so there was a visiting American student. He just rocked up to do some work. I can't remember what it was, and I was just showing him around the telescope and said, oh, this is the work I'm doing, blah, blah, blah. And these are my new files of consecutive bright pulses. Let's look at one, see what it looks like. And I clicked one, and this is what I got to show him. And you can't quite see it there, but there's 6 bright pulses in a row there. And that turned out to be the biggest that I found in that whole 10 million pulses that I observed. And I just pulled it out randomly. The chances of that, and this is all part of my thesis, that the chances of this happening, it turns out that a bright pulse typically happens at the time anyway, happened at about 1 in 180 pulses. So to get 6 in a row, if they're all completely independent events, was 1 in a billion or something like that. The chance of getting 6 in a row was really, really very small, 180 to the power of 6, whatever that is. So very, very small. So the chances of observing one of these is just 1 in a billion. I actually observed 2 in my 10 million pulses. That should not have happened. So what that says is that the assumption that I made was that they were independent events is wrong. So they're linked. The brightness is linked somehow. So there's something happening on the surface of the pulsar that's causing it to stay bright for a number of rotations. And that's about half a second when you add up the time. It's a long time for a pulsar. So what's happening on the surface of the pulsar? And this is where things get really interesting, because the emission properties of a pulsar are not well known. And there's quite a few emission hypotheses around. And this one has put a few, has sort of pulled them out of circulation, a couple of them, because it just, you can't explain it. So, and there's a few, and I'll get into some of the ideas a bit later if we've got time. Okay, now, if you've got an object the size of 20 kilometres across spinning 700 times a second, they can be extremely accurate clocks. And in fact, some of them rival atomic clocks in precision. So there's a project going on at the moment to find all these highly accurate, some pulsars. The Vela pulsar is not hugely accurate, but the faster they go, the more accurate they are. And have a whole bunch of them, a cluster of these pulsars, and monitor them all the time, and use that to monitor and compare our own clock technology. But also, gravitational waves gravitational waves are predicted to exist, but no one has worked out a way of seeing one yet. And so there's a number of experiments going on trying to detect these gravitational waves, which should occur when black holes collide and stuff like that. And they should be around there, but we just can't detect them. But one of the theories is to use these highly accurate neutron stars. We should be able to pick up the signatures of gravitational waves. So that's happening in the background. There we go, gravitational waves. Alright, so let's talk a bit about, that's pulsars. Let's talk a bit about atomic clocks. Oh, just on the pulsars before I finish up on that part was, I submitted my thesis. That consecutive bright pulse discovery was actually very significant. And so I I published a paper in the Astrophysical Journal on that, so separate to my thesis. So that was actually made a difference, which was a really, really rewarding thing. And research is fantastic because it doesn't cost you anything. I said, how much is this going to cost me? And they said, bring a pen. You know, because you're not doing lectures, you're not having exams marked or anything like that. You're doing research, you're using the tools of the university, and then you're giving the university a good name, so they love you. So research is really good. It's fun too. Got to get your hands dirty though, up there at the observatory. It's pretty good. So, okay.
Can I just ask a question?
Sure.
Why do you get that extra brightness?
All right, you've asked the question, I'll tell you. Okay. I mean, the answer is I don't know.
Right.
But I have a hypothesis. Well, actually, I don't have. There's a number of hypotheses out there, and that consecutive bit has sort of blown a few of them out of the water. But one I like, the one that works best for the data I have found, is so you've got this pulsar. So imagine a sort of a bunch of neutrons, really hot. There it is. And then above that you've got this magnetosphere, sort of a plasma, and yeah, and this is imagine this is one of the poles. Now you've got this emission thing that no one really knows is happening, and it's going out there. Now the bright white goes brighter. You know, there's this different theories that there's emission, different layers of emission, and maybe they just randomly line up, and it goes a bit bright. That doesn't really work. But the one that really sort of clicked when I read it was a Russian guy who sort of hypothesised it, was that the emission actually occurs in the gap between the magnetosphere and the star. And the emission occurs there. And then and every other hypothesis says that the magnetosphere is where the emission occurs, but what he's saying is that it occurs in the gap between the pulsar and the magnetosphere. And the magnetosphere...
Excuse me.
You just stopped the major word. That was amazing. You didn't hear what I said there. That was the most important word of the night. The magnetosphere blocks the emission from in the gap between the neutron star and the magnetosphere, like a cloud. And it's sort of the normal emission. It sort of leaks out around the field lines, and then occasionally, this is the theory, that there's a gap opens up in the magnetosphere and lets the radiation through, and it can stay open for a number of seconds, and that's when you get the consecutive bright pulses. So here, that was his hypothesis, fairly new, and then my data just fitted it beautifully. You could have almost predicted these things were going to occur. So that's all quite exciting. We're sort of perhaps changing changing the thinking of the emission process in pulsars. So still going on that one. My arm's being twisted to do a PhD, so we'll find out. Okay, so to measure pulsars, you need an atomic clock, because these things spin very fast, very accurately, so we need to measure them very accurately. So this is sort of a part of it. Now we have a lovely atomic clock out there called a hydrogen maser, which I understand you may have seen if you've ever done any of the tours out there. And again, it's about that size and blue. Now, hydrogen masers aren't strictly speaking primary standards, which means the second is defined by the transitions of a cesium atom. So you need a cesium clock to define your second and measure your perfect second. Now, the problem with cesium as a clock is that it's, over a short period of time, it's pretty dodgy. And by dodgy, I mean, a trillionths of a second here and there, but over a short period of time, it can waver around. Over a long period of time, like a year or something, it's fantastic. But over a short period of time, a hydrogen maser is actually a far, far more accurate piece of equipment. So if you're timing over a few days, you can, and hydrogen masers are adjustable, so you adjust them to a cesium standard, and then then you can do some really short-term measurements with the hydrogen maser. So that's why you find hydrogen masers at telescopes. And we use the global positioning system to set them to the right time, which we'll come back to. So, okay, back to, if you had to ask the question about what time is it, if you had one clock, that's all you had was one clock. You have no idea what the time is. You can't tell, is my clock running fast or slow? You have no idea. And even with two clocks, you don't know which one is fast and which one is slow. You need 3 clocks at least. And if you've got a bunch of clocks, what is the most accurate of all those, let's say you had 20 clocks and nothing else. What is the most accurate of all those 20 clocks? It's the average of those 20 clocks. Even if one is really bad and dodgy, if you average those 20 clocks, that average is more accurate than any of individual clock. So we have around the world 230 plus atomic clocks which monitor time, and then we average them each month. All the data is averaged, and then that average is then used to see which ones are going fast or slow. And if there's any really bad ones, they'll drop them out of the consortium. That's called coordinated universal time. Interestingly, we measure time more accurately than any other constant. Anything else, length, mass, anything. We can measure time. Don't know what the latest is. I mean, well, I think we're sort of measuring down to about 10 to the minus 18 accuracy. I think is some of these latest. The problem is though, the problem you get, and with accurate time is it's bloody Einstein's fault actually. You've got relativity, which I'm sure you've heard of. You've got special relativity and general relativity. Now, in a nutshell, special relativity is that the faster you go, the time slows down. So the velocity that you're travelling affects how time goes. That's special relativity. General relativity, in a nutshell, says that gravity will slow time down. So a clock on the floor of this place, a clock in this place here compared to a clock down at the docks, the clock down at the docks will run a bit slower than a clock here because gravity is stronger down. The closer you are to the Earth, the stronger it is. And this actually, I've actually tested this. It's true. I have a rubidium clock at home. It's the universities, they don't use it anymore, so I keep it ticking in the rack at home just to keep it going, just in case they ever want it back. And but when I moved it from the observatory to my house, and they were at different altitudes, I noticed after about 2 weeks it was actually losing time. And that was because they were at different altitudes, and that was because gravity slows down time. And just so you know, I'm sure you're all familiar with the global positioning system. A bunch of satellites orbiting the Earth, sending a pulse per second down every second, and your device takes that, it knows that it's getting a signal from that one there, and it knows it's getting a signal from that satellite there, and it works all it out basically from how long it took to get from there to there, and works out where you are on the Earth. Now, the other beautiful thing is with the global positioning system is that once you know where you are on the Earth, you can then, if the device is designed for time, you can actually work out what the time is where you are on the Earth very, very accurately. To within about 10 nanoseconds, if you've got a good one. I'll come back to this. So, now the interesting thing that's right, I was about to say, the satellites, the GPS satellites are all got atomic clocks in them, okay? But they're orbiting the Earth. And it turns out that because there's less gravity up there, they would run faster. So they actually deliberately run them all slower than normal, what we would run a clock down here. And if they didn't do that, GPS would not work. Completely would not. We'd be a kilometre out. So Einstein got that nailed in 1910 or something. It's just unbelievable. So anyway, the universities, we got this fantastic clock at Boulder, Colorado, 1 second in 20 million years. But this is one of the ones that I sort of enjoy assisting and looking after. That's the hydrogen maser. We've got it currently at the moment drifting about 0.2 billionths of a second per day. And what we do is we monitor it against the GPS time over a month or two, and you can see a delicate drift happening, and then we can correct it and bring it back. And the goal is to the general goal is to keep it under a microsecond a year, a millionth of a second a year, but I like to do it better than that. So I'm a stickler. I like accurate time. So there it is. That's how it looks like a fridge. Fascinating device. It's built like a tank, these things are. The engineering behind them is brilliant. It's everything runs, the guts of it runs in here, and the mazing that happens, mazing is the same as laser but with microwave, so it's microwave amplified stimulation with whatever, emitting radiation. But it has to all occur in a very, very, very strong vacuum, and that's the real skill, is when you have to play with these things, you have to restore the vacuum in these chambers, and it's a really hard thing to do. But anyway, move on. Oh, right. So these are a couple of my little toys that are in my garage. So this is the speaking clock that I've been talking about here. So from top down to here is the speaking clock, essentially. I crushed it up into sort of taking up half a fridge. And so we have a couple of oscillating units that are designed, 5 megahertz oscillators that are designed to sit there ticking away if it lost the signal between itself and Melbourne, so it lost contact with the cesium clock, so it would keep ticking over. These disciplined oscillators, so they discipline themselves to the signal that is coming in, and then if it stopped, it would just hold it there. And there's 2 of those. This is the main sort of console computer control unit where you would put in the time and the leap seconds and everything, and then this is the voice unit, and the time is shown there and there as well. The rest of this is other equipment that I've got hold of. That one there is the HP. It's built back in the 80s. It's a sort of better version of that. Oh, it's just a frequency counter. It's actually a timer, and it is a frequency counter as well, but it's a timer. So basically you give it a stop signal and a start signal, and it will time how long it took for between the stop and the start. Now this thing is built with TTL logic, built back in the 80s. It's about this, and it has a resolution of 20 picoseconds. That's 20 trillionths of a second. So I can quite comfortably measure, that's a resolution, I can quite comfortably measure an accuracy of down to that level. So like you can be putting a pulse through a cable, and you can run it into the start, run it out into a meter cable and run it back in, and quite easily measure the time it took for the signal to travel along the cable. It's nothing. It's not quite the speed of light, but it's getting pretty close to it. An amazing piece of equipment. Back in its day, it was worth about $30,000. I picked mine up on eBay for $250. Okay. It cost me $400 postage to get it from America, but you know, it is one of my. I love that unit. It is just fantastic, and it is built so well. Again, the manual's this thick. All the circuit diagrams, you can go in there and fix it.
Should have flown over for a holiday abroad.
Just about, yeah. And this is its partner, this is its friend, this is the signal generator, which is a digital signal generator, so you can generate sine waves, square waves, triangular waves, and all down to 0.0001 of a hertz if you want. Very large and very, very accurate. They all take in the back. They all take a 10 megahertz standard in, so you feed that from a GPS DO. Yeah, you've got a highly accurate piece of kit there for measuring time and frequency. That I built myself. It's basically a GPS disciplined oscillator. I built myself 2 atomic clocks actually from parts on eBay. You buy the rubidium standards, and you buy some display, and then a microcontroller, and program it all up, and bang, you've got yourself an atomic clock. So that's all fun. That's the J car. Everyone loves that clock. That's a J car clock. It sits there spinning around. Mesmerizer, it's called. That's an old-fashioned. I collect old HP gear like that from the 80s. I love it. That's an old frequency counter with Nixie tubes in it. Beautiful piece of equipment. And that's the online rubidium clock, which sits there ticking away.
And don't tell me the clock in the oven in the kitchen is a bit faulty.
Clock in the oven in the kitchen.
Yeah.
My oven.
Plumber's leaking tap never gets fixed.
Oh, well, the oven doesn't have a clock. It's a completely crap oven, so that's why I was looking at what. But I'm with you now.
VCR flashing 00.
Yeah, no. When the leap second happened the other day, in case you didn't know we had a leap second, I should hope you know we had a leap second the other day. Qantas certainly do. Yes, no, I went around and dutifully changed all my clocks. Now, this is my other little treasure. So I was talking about my speaking clock to a friend who works for Telstra, and he goes, I have something you might be interested in, Jim. Now, prior to this beast, this is what used to keep time in Hobart. There was 5 of them, one on each level in the exchange that was on the corner of Davey and Harrington Street. And it's a beautiful pendulum here swinging away, and you can, there's a little magnet there and a little unit here, you can speed it up and slow it down. And it's a regulator, and they all talk to each other, and the time used to get distributed around Hobart. Anyway, when that was all decommissioned, he picked it up, got it like I did with the speaking clock, and he said to me, look, it needs to go to a new home. It was just sitting in his garage, locked away, not doing anything. So he said it needs to go to a good home. He said, I'll sell it to you, but just make me the promise of if you sell it on you first, you offer it to me first. So but I'm not selling it. So so this ticks away now. Now what I've done with this one is this piece of old 50s technology here is pretty hopeless. And the way it did it was, you may think that a pendulum will tick the same rate no matter how high it swings. That's what they teach you in basic physics, that if even a pendulum is swinging here, it will take the same time as if it's swinging here. That's actually not strictly true at the precise levels. And so what this did was, to slow down or speed it up, you would sort of either turn this on as a magnet to make the pendulum swing more, or push on it to slow it down, and you could adjust the rate of the pendulum using this thing. So I can do better than that. So one of the atomic clocks I built with a microcontroller, what I did was I made it so that it pulses on the second that little magnet there, so just a coil. And so eventually the whole thing sinks in with it, and then it sits there keeping absolutely perfect time to an atomic clock. So that's been ticking away, hasn't lost or gained any time for months and months and months, and then the leap second had to come along, and I had to literally go stop the pendulum for a second. And yeah. So yes, I bought this little transmitter. I broadcast on 107.7 from Old Beach, so yes, if you're driving past, you can. It's not a good location as I was in South Hobart, but it's there. That's not against the law, is it?
Probably. Only if you get caught.
No, power's too low.
What is the minimum?
100 million.
I mean, I assume that if they're selling it over the counter, that it's legal.
Yeah, probably not a good assumption, but anyway.
Yeah.
Not as bad as the old days on the PMG, ran it.
Well, that leads me to another story, which I was talking to you about. Mustn't forget I talk about this. So I started my pulsar work right at 1440 megahertz. After 3 years of observation at that frequency, and we picked that because it's a good frequency for the Vela pulsar, but it's also very clear. Like 14 around that frequency is generally kept pretty clear because it's reserved for radio astronomy. Because the hydrogen line is at that frequency, but that's another thing. Anyway, so we picked 1440 and got about 3.5 years of observations done. Came in one weekend, and there's this block, just right on. There's my frequency there, and it was going block of interference. It's just I couldn't do it. I couldn't observe. So I got the gear together, got a car, went for a drive, like that guy did. Whoever it was that tracked down my thing, we got this receiver. It was literally just a little receiver. It looks like a bazooka. And you put it on there, and I went for a drive to try and track this interference. And I ended up standing on the end of the runway near 7 Mile Beach, but just a bit to the east of it. And I'm glad that plane didn't come into land while I was holding this thing, because tube here. But anyway, there was this signal booming in from down that way, and it turned out to be a transmitter from the police department. They'd just installed it, and it was transmitting to be received on the top of Mount Rumney, I think. There's some transmitters there, but that receiver hadn't been turned on, so it wasn't responding, so it was transmitting at full bore. And so this is radio astronomy here. We should have been notified or say, hey, can we use this frequency? And what it turned out was that the ACMA had done the right thing and contacted the CSIRO, and the CSIRO didn't contact the university here, and so the communication, an email wasn't sent when it shouldn't have been, so we could have objected. which meant that they went ahead and spent all the money and spent their $30,000 or whatever it was they spent on the transmitter, and basically I had to stop the experiment. That was it. I did actually go in and speak to them, and they actually turned it off until it was fully commissioned, like right to the last day. They gave me an extra 2 or 3 months, which was enough for me to sort of wind up my experiment. But yeah, that was so interference terminated my experiment, which was after 4 years and the longest data study of single pulsars and pulsars. Okay, now this original presentation, I've done this one before, variations of it, so you may know some of this, but I don't know if you guys have ever seen the Thunderbolt.
Thunderbolt.
One of the best value for money GPS discipline oscillators you can buy. Absolutely fantastic. You just plug it in and off it goes. But the thing is about it is a very accurate device as far as there are GPS DOs and there are GPS DOs. So as far as you can get them for about $200, and for value for money, that's the one to get.
Why don't they got the name Thunderbolt?
I don't know. Now, like any good person who enjoys clocks and who has access to a hydrogen maser every day, so I found some spare time for myself and went, what's going to happen? What happens with the GPS and the maser over a day? So the maser's nice and accurate, running for a day or two. What's going to happen? So that's the residual, all the differences between time between the maser and the Thunderbolt. This is in nanoseconds. Okay, up the side here, so there's 0 there, 5, 10, 15, 20, 15, 20. So it does a pretty good job, but I think the next slide, no. You can see there's a pattern. See they're going up, this is 24 hours, so from there to there's 24 hours. So you can see there's this pattern.
Lunar tide?
Hmm?
Lunar tide?
No, it's the
No.
ionosphere. It's the sun rising and setting. It affects the ionosphere. And it affects the signals travelling down on the GPS, arriving at the GPS unit. And so it does actually affect. So that is, and you can compensate for it. If some of the more fancier units do, that you pay big dollars for, will compensate for that.
So you're saying never try and plot your position in the morning, come back in the afternoon?
If you want to either get the time or your position, you do it over 24 hours. Okay, you average it. So when you turn, like when you turn on a Thunderbolt or whatever, it will. Let's assume it doesn't know where you are. It will go into averaging mode. So it'll sit there, and for 24 hours, it will monitor where it thinks you are, and then it'll average out over 24 hours, and then it'll go, right, you are here. And then all of a sudden, once it knows where you are, it will start spitting out highly accurate 1 pulse per second signals. And as you can see, with a Thunderbolt, you can expect to be within, the majority of the time, within 5 to 10 billionths of a second of coordinated universal time, which is pretty good for a couple $100.
$200.
What's that in terms of positioning?
Well, the position's locked, so it's stationary. So you can, with a GPS, the GPS can either tell you where you are or what time it is. So usually they're designed for one or the other. So if your average GPS unit in your car or something, it'll have a clock on it. Usually they can be quite a few seconds out because they're focusing on where you are. They care about time. Whereas the thing like the Thunderbolt is designed, the unit that's in it is designed to give you time, and position is less important. So it sits there for about 24 hours, averages where it thinks you are, and then locks that in, and that average is a very good location. You can get it, it'd probably be down to within about this much. Very good, over 24 hours.
A couple of years ago, Silicon Chip did one as well that you could build as a kit. Have you heard anything about those? Or?
I haven't seen that one, but look, it's not hard. Like the concepts behind it all, it's really, I mean, I showed you on my, that was a whole kit, microcontroller. Actually, it was a radio amateur from New Zealand, Murray Green.
Yes.
Anyone know Murray?
Time nuts.
No, obviously.
Yeah, bright boy.
I think
Very.
he argued with the Silicon Chip and they made some modifications. So it was one of those things.
He's a genius, that guy, I can tell you, absolute genius. I learned so much from him. He built the original controller that's in there that I built. It was from his design. But yes, the concept's not hard. You get a decent crystal oscillator, oven controlled one, you know, that you can control, voltage controlled crystal oscillator, and you set up a feedback loop with a microcontroller, and you have a GPS board. You don't build those, you buy them, they're dirt cheap, and you take the 1 pulse per signal coming in every second, and you use that to discipline your oscillator. It's quite a fun little project. There's lots of things to do for it. But some of the boards are better than others, of the GPS boards, and some of them are, do a much better result for what they're doing. So, but if you want to just buy one, now this, by the way, also spits out 10 megahertz out the back, which is of course once it's locked in is a good 10 megahertz as you're going to get, except from a hydrogen maser, of course. So that was interesting to look at the atmospherics. I found that quite interesting. I know you all know, but I just explained the GPS. I consider this, and others do, the greatest invention in the last 20th century. But explaining about that and how it works. Okay, done all that. Done that. Okay, so we don't tell time by the rotation of the Earth anymore. We look at time is now measured by these atomic clocks, and we keep the Earth in sync the clock's in sync with the Earth because the Earth's slowing down gradually. We have to introduce a leap second every now and again, which the last one was just the other day. And unfortunately, now being an astronomer, I've always been very strongly of the view that we should keep these leap seconds, the Earth in time, our clocks in time with the Earth. But after the last one where major airlines had outages right around the world, it wasn't just Qantas, it was a major, Amadeus was the system. It wasn't prepared for this sudden jump in the time, and it just...
They should have been, it was a kernel that could have applied.
I know, but they didn't.
So fire the sysadmins, don't fire the computers.
No, but my thoughts are now, there's a debate in the time world about whether we should be keeping leap seconds going in. Okay, and the debate is, one, yes, keep doing what we're doing, or no, stop doing them. And then do one when it's a leap minute, or when it's an hour. When it's an hour, just don't do that, saving 1 year, whatever. There's all sorts of options. And they're arguing about it, and they were going to reach agreement last year, but they put it off for another 5 years because it's too hard. I've always been on the astronomer's side, as in keep the leap seconds, but after this one I've been thinking, I'm sort of weighing up now. I mean, I agree with you, but the problem is leap seconds aren't like daylight saving that happen twice a year. They happen, the last one was years ago, so yeah, it's a problem.
Better than the old days when they used to adjust directly to the clocks.
Sorry, what was that?
The world was so technical now, you can't stop to do adjustments.
That's it, everyone relies on these timescales now. I mean, we've got other, the thing is, there are other timescales. There's an atomic timescale called TAI. There's a GPS timescale. They don't have leap seconds in the GPS timescale. So we could jump to one of those and use those. The problem is political. You've got to get every law changed in every country to say we're no longer using UTC, we're now going to use TAI. And everyone has to do it all at the same time. It won't happen.
Can I ask a spurious question?
Yeah.
No, I don't want to divert what you're saying, but we're talking about GPS. What is the future of GPS? If you read the populist press, you get the idea that the United States government has the mortgage on the satellites sitting above. They've got a finite amount of time left in them, and they're not being serviced. The Russians, on the other hand, apparently have got an alternative.
They have, yeah.
Oh, sorry, yes, the Russian Federation.
The Russian has, yeah.
Yes.
And there's another one going up as well. The Europeans are putting up a new one as well.
And the Chinese. And the Chinese.
Actually, yeah, I think the Chinese, I did hear that was just the other day. Yes, they've just started theirs as well. So, yes, it is a little bit scary from an American's perspective, because when it first was turned on, they deliberately made it so that you couldn't get accuracy of more than about 200 metres. And it was Clinton. He pulled the plug on that. He said, no, everyone can have full accuracy now. And the commitment was made that, no, we will look after us and keep it going. But, you've got to have a backup. So I think the European one is probably a bit of a saving grace there. As a technology, it's just, I'm astounded, the things you can do with that, the fact it's got GPS built in, just incredible. I wouldn't have even thought about it a few years ago how good it is. That's pretty much all I've got. There you go, Aaron. How you see it?
Can I ask a question that's been bothering me? When you said the gravitational force changes time.
Mm-hmm.
And you can prove this by taking X clock, whatever it is, and putting it down here.
Yep.
Is the gravitational force changing time, or is it changing the way that the timekeeper works?
No, it's actually changing time. That's the, this is Einstein's theory of general relativity. This is a complex topic. I'm just trying to think of the best resource. There was a program on TV many years ago, and they sort of, what was his name? Peter Ustinov narrated it. And it was called Einstein's Universe. There we go. It was back in the 80s, and that was a really they explained it with bowling balls on trampolines and stuff like that. So yes, what happens is we've got this. We're in space. We have time with this thing that we call space-time. So space tells matter how to move, and matter tells space how to curve. So what that sort of means is that something that's heavy actually changes the nature of space-time, and that's what actually slows time down. And yes, it's not just altering the physics inside the, and you can do that because you can do experiments to prove it. Because you know, if it was gravity, if you turn it upside down, it would do something different. You know, because it's a one-way force. So, and you can take multiple different technologies and do the same things, like a hydrogen maser or a cesium clock. And cesium clocks and hydrogen masers and all that, they're all basing their time on the vibrations of the atom, and that doesn't change with gravity. You know, the nature of gravity's not strong enough to do that. So it is, you know, and it has been shown many times, and that's pretty much what Einstein's theory of relativity. And Einstein's not really been proven wrong, ever. So yes, no, it does. I know it's weird, it screws with your mind. It really does.
Somebody was worried the other month they found something that didn't quite agree with his arguments, but
Oh, you're not thinking of the
Tachyon, was it?
what? Sorry.
Tachyon.
No, not the tachyon. The neutrinos, the faster than light neutrinos. Yes. Yeah, no, that was an interesting story. Like, basically, they were firing off these neutrinos, and then 600 k's away, wherever far it was, they were detecting them, and they were getting there faster than the speed of light. And they couldn't find out what was going on. They did this experiment time and time again, same deal. So they eventually published and say, look, we can't figure it out. We'll just open it to the community, and that's when it all hit the media and everything. And if it was right, if it was true, physics as we knew it would have just died in the bum. So we knew there was something wrong, and you know, everyone was saying there was a measurement error or there was something wrong with the measurements. But they were really good anyway. It turned out to be a cable wasn't properly plugged in. And it was an optic fibre cable that hadn't quite been plugged in enough, and it was just delaying the time measurement, which made the thing seem like it was going faster. So yeah, but it took a lot of work to discover it. They plugged it back in and bang, fire problem solved. Thank you very much. But that's science, you know, that's what science is about. Science is a process of discovery, it's all it is. And so you're quite happy to put your stuff out there and say, do your best to trash this, you know, and if your pet theory gets trashed and the evidence doesn't support it, you walk away from it. Yep, no, that was wrong. Move on.
And all the great discoveries have been done by accident anyway.
By
accident anyway. If Röntgen hadn't been so untidy, you'd never discovered X-rays.
well, yes, no, I wouldn't say all the discoveries,
No,
but
most
certainly some.
an awful lot of them are just done purely by accident.
Yeah,
Someone notices something.
well, that's it. Is that an
didn't seem quite
accident
fit.
in the sense, yeah, I mean, I'm not saying that, you know, my consecutive pulse thing will be a great discovery, but it was an accident. You know, it was that, you know, someone noticed and said that would be interesting to study. It was just this tiny little sort of thing that said this could be a good idea.
It's good observation.
Exactly.
You
Yeah,
did notice it, yeah.
yeah.
What, hydrogen maser, are you able to explain in like block diagrams how it works, and the cesium maser, or?
Well, basically the way an atomic clock works is the cesium clock, for example, the cesium atom vibrates at 9.8 whatever billion vibrations per second, and it's defined like that. So the second is defined as that number, vibrations of the cesium atom or transitions. So what what you do is, now let me get this right. You stimulate the cesium, you heat it up first, and it's stimulated with I think it's microwaves. In the cesium clock, it's the same as the hydrogen maser, and then that's stimulated. Then, now let me think about this. You then have an oscillator that tries to lock into that frequency, and it's got to hunt for it because it's very hard to detect this frequency. So it's got to hunt, but eventually it will lock in onto that frequency. And then once that oscillator, and that's just a plain old boring crystal oscillator, it's nothing fancy. But quartz is pretty good actually when it comes down to it. Quartz, a good, well-cut crystal, is actually a very, very reliable short-term oscillator. Not crash hot over a long period of time, but over a short period of time, like a second, it's really good. So they lock in onto that vibration that's caused by the microwave stimulation of the atom involved. So, yeah, not my field, so I'm not.
No, that was how they actually measured, I suppose, the transitions, but or locked onto them. If you
How do they lock onto
How
them?
do they detect them to lock onto?
Yeah, no, don't know.
All right.
Don't know exactly. Yeah.
I like that one.
Yes.
So,
I do know, but I've forgotten. Like it's,
Okay.
I do remember reading about the intricacies of how these things work, and it was there is a detector there that picks up, but I can't remember
Yeah,
what
I
it was.
just
Whether it was
often thought, okay, cesium does its thing, but then you think, well, how do you actually, do you wind a
Detect.
coil around it or what? You know?
no, it's not.
It's
No.
not really that.
Google it.
Yeah.
Wikipedia, that's
My granddaughter's answer for everything is Google.
You were saying that the cesium clock isn't that accurate short term,
Yeah.
very accurate long term. Is there any reason why there is that variation? Like, is it perhaps some spots
It's
or-
because it's a large atom. It's a big mother of an atom. You know, it's
and so
and that
so
just
gravity can't affect it.
no, it's nothing to do with gravity. It's a hydrogen maser is really good because it's the hydrogen atom is very small. It's the
Yeah.
smallest one. But we've defined our second in terms of the cesium atom, and so there are slight. So that's the definition of our second. So, but it is the cesium over a long period of time is better. But over short periods, simply because it's just a large, cumbersome sort of atom, it's not so crash hot over short periods, like a minute or an hour or something like that. And even these hydrogen masers and these cesium standards and everything, whatever they're doing, they still have this crystal quartz thing sitting there vibrating, delivering the actual signal out to everything. So they're all driving that crystal oscillator. So they're nice good old quartz crystals, as long as they're well cut, they do a very, very good job.
Yeah. Good stuff. Any other questions for Jim?
Right at the beginning you mentioned the old Telstra talking clocks synchronised to a cesium clock somewhere on the mainland.
Yep.
Was there an allowance for delay down the phone line?
Yes, good question. And absolutely, they had to measure the delay because there would have been quite a decent
That's
delay.
no point in using cesium.
Exactly. So, and do you know how they did it? You know, and this is going back, in the 80s when they set this thing up. Do you know how they worked out what that delay was?
Time delay with different quantities.
No, not accurate enough. No, they booked an aeroplane seat and flew the cesium clock down, working. So kept it going, put it in the aeroplane, flew it down, and measured it and compared it back to the one back home and measured the time. And that's how they did it. They had to do it once for each state. And it was Graham himself who did the flying around to each of the capital cities in Australia and told me the story of it. So I asked exactly the same question, how'd you do it? He said, I just got on the plane with a cesium clock and a car battery, It was back in the old days, and that was
So, I mean, would Western Australia be further out because of the plane trip, flying at the higher altitude?
there would certainly the clocks would be out because of general relativity, but it's only nanoseconds, so measurable, but certainly for the purposes of a speaking clock, they just needed to the nearest millisecond, really.
I believe back in the early 80s, they used to actually synchronise all the clocks down the east coast by using the timing pulses on the ABC, the line and the frame.
Yes, the TV had. I don't know if it still does. Well, it's analog TV, so they're still doing analog TV, but not for much longer. Yes, I think you're right. The signals on the ABC television were generated using a rubidium frequency standard, I believe. So
Rex listens for Newcastle television, which is rubidium locked.
yeah. Now rubidium's like It's an okay standard. Like, it's nothing like a hydrogen maser, nothing like a cesium clock, and your GPS DO is probably going to be better than a rubidium, to be honest. So, and yeah, the ones I've built are all rubidium ones, and that one you saw on the thing there at the bottom, that old HP unit, that's a rubidium one. That's probably the best you can get, actually, as far as rubidiums go. Yeah, it's I mean, what they use rubidium for now, and that's why you can pick them up on eBay fairly cheap. You can pick up a rubidium unit, you know, it's a crystal oscillator, you put some voltage in and you'll get 10 megahertz out once it's locked onto itself, and they're pretty bloody good too. And that's, you don't need a GPS or antennas or anything like that, so they're very handy. You can pick them up for, I mean, I'll pick one up for $80, but they fluctuate. But they're quite good, but they were used in telecommunications. So each, I mean, the reason that the bandwidth that you're getting over these things, and you guys know all this, is because of the clock technology. The accurate clocks that are in each base station. So the more accurate your clocks, the more the more bandwidth you've got to stuff down the communication wire. So the reason that, say, Telstra's next G or 3G is better than 2G, and then the next one coming along, LTE, is 4G is better, is pretty much because of the clock technology driving behind it. So that has been developed now, a chip scale atomic clock, where you can buy for, it's about this big now, it's an atomic clock. Not as accurate as rubidium or anything like that, but still about that big. I look forward to the day it can go on my wrist, so I can have an atomic clock on my wrist. And that will happen, there's no question about that. But yes, as clock technology improves, so will our bandwidths over wireless will improve drastically. And obviously optic fibre cable as well. So when they pull down these old base stations and move to the next technology, you can pick up these GPSs and time standards and rubidiums and all that, and they're great buys if you know what you're looking for.
There was a problem with the television standard being sent down, because when it was on broadband, everything was pretty close to the mark. They could work out what was happening. But then when it went to satellite, it took longer.
Yeah.
And they were having problems because of the heating of the atmosphere on hot days.
Okay, yes.
The path would take longer.
With the same as the GPS. Yeah.
So they had to think about that again. And that's when each state got its own rubidium.
Yep. And
they would coordinate it at a certain time of day, and I forget when it was automatic, but it was something like midnight or something like that, when the temperature of the path could be relied upon to be uniform.
Okay, that's interesting.
I remember I was talking about it when you'd see this.
Yeah.
So I remember the day that we installed the little oven type oscillator in the AV van. It was great, 19 inches wide but so high, chamber, and that was it.
Yep.
It changed our stability no end.
Yes, I've got a few. I've picked up like whenever the observatory sort of has a bit of a clean out, or I was there gathering. No, you don't want that anymore. That's great. So I've managed to collect a few things.
Recycling.
Yeah, I don't like to see things get thrown. And I did mention before, someone was saying they had capacitors for sale. There was a hearing centre just along from where I worked in Telstra, and they were having a big clean out, and they were just chucking stuff away. And this big skip bin, and I went inside and peeked over, and I thought, whoop. So I went inside and said, can I raid your skip bin? I said, yeah, no worries. Anyway, there were these resistor packs everywhere, little packs of resistors, and so I thought, so I grabbed every one I could find, and I have it in a suitcase at home still, and it is 20 kilograms of resistors. Everything from 0 ohms up to 10 megs or whatever. And the old big ones with the colour codes on them.
Quarter ones you can see.
Yeah, ones you can see, quarter watt ones. So if you need a resistor.
Yeah. When it all goes surface mount, we know where to come.
Yeah, just track down the speaking clip.
I think I've got some 2 watt resistors, haven't I?
Yeah.